Another example of a slightly more complicated controlled process, for understanding purposes, would be you changing lanes while driving. You would be the controller. The lane that you want to be in is your set point. The steering wheel would be your control variable, and your current position on the road would be your process variable. Your eyes are your feedback. You adjust your steering wheel according to many factors, such as the angle of your wheels, possible wind disturbance, the position of other vehicles, that sort of thing. You don't do hundreds of calculations to determine your point of attack. You intuitively, after years of driving, know what you need to do to safely switch lanes. Because you are not blindfolded when you drive, your eyes give feedback to your brain, allowing you to control this process through reference feedback. This control is considered a closed-loop process. But consider a blindfold. You'd have no way of knowing where you are on the road. This type of control would be called open-loop control. Obviously a much more difficult process to control, and on occasion, you may run into this type of control in your career. In an industrial plant, since there are many factors that we need to consider, we need a robust controller that takes our parameters into account and does hundreds of calculations to determine where the process is and where it needs to go. Say we need to control gas flow through a pipe. The set point of gas flow is calculated based on a calculation of some factors. This set point can change at any time based on the parameters used in the calculation. We will control this flow based on a modulating valve. In this case, the more open the valve, the more gas allowed to flow. The requested position of the valve is our control variable. Downstream of this modulating valve, we have a flow meter that will measure the gas flowing through the pipe. This is our feedback, or our process variable. In this example, we are going to use a PLC function block in order to control this process. Our PID block will be able to use the parameters we specify to determine the controller's reaction to our process. Let's take a step back and talk about the parameters that we will be adjusting for our control. First, the PID term, as stated earlier, stands for proportional, integral, and derivative. These parameters can be used individually or collectively, meaning you can have just a proportional controller, a proportional and integral, a proportional and derivative, or of course, a proportional, integral, and derivative controller. Each of these parameters is enabled and adjusted individually, and each controller type would be used for specific purposes, each parameter having a specific impact on the way the controller functions. To sum it all up, we, as control engineers, need to control processes, and in order to do that, we use devices available to us in order to facilitate that function. The standalone and integrated PID controller is the most widely used device for that purpose.